So welcome. So this is the second chapter in this section, which is waves. We did about oscillators last time, and now we're going to do about waves. And what we're going to, first of all, realize is that a wave is made up of a material, or rides on a material, which can be considered as a family of oscillators. So if you like, if that's the surface of a water, I could imagine there's a whole bunch of little droplets of water, and there's some kind of connection between the two. They are oscillators, but they're connected together, so the energy can go from one oscillator to another. So that's an oscillator, and next to it's another oscillator, and next to it it's another oscillator. And when you get, in the case of surface of water, you get surface tension. In the case of a spring, you get the elasticity of the spring. When you have some kind of connection between the oscillators, then you can get the energy transferring, and you get a wave form. So a wave is made up of a family of oscillators that are connected together. So everything we learned last week applies to one of them, and now we're going to say what happens when you connect them all together. And what we're going to talk about today is waves can be classified as four main types, and that's going to be transverse or longitudinal, and we're going to have a wave train or a wave pulse, and we'll get to that. And then we're going to talk about important characteristics of a wave, and we've met amplitude, and we met period, and we met frequency when we were talking about oscillators, and we can talk about a wave having an amplitude, and we can talk about the oscillators of a wave having a period and a frequency. But the wave itself would have a wavelength, and the analogy of frequency to that would be the wave number and the angular wave number. So for oscillators, we had amplitude, we had period, we had frequency, and we had angular frequency. And now for a wave, we'll still have the same amplitude. We won't have wavelength. We won't have period, we'll have wavelength. We won't have frequency, we'll have wave number. And we won't have angular frequency, we'll have angular wave number. So these analogies are really useful. This is in meters, that's in meters. This is in seconds, that's in meters because it's a wavelength. This is in 1/seconds, which is hertz. This is in 1/meters, and there's not a special name for that. And this is in radians per second. And by analogy, what do you think this would be? The angular wave number would be. Angular meaning radians. Now look at your analogy. What's it over?
Meters.
Meters, yeah. So I find, especially with new terminology like this, little things like this really help me. Because I only need to know one side really well. If I know the left-hand side really well, I can figure out the right-hand side if I get a little bit confused. So then we start playing with this, and we start talking about one-dimensional waves on springs. We talk about wave speed, a traveling wave model. That's a mathematical model. We talk about sinusoidal wave velocity, waves on a string, speed of waves on a spring, reflection of waves, transmission of waves. We talk about some energy effects, and we talk about the linear wave equation. We kind of get to the linear wave equation, and we just show you the form of it, but we don't play with it. So that's where we're going. There are really two types of wave. There's longitudinal waves and there's transverse waves. Longitudinal waves can happen in lots of materials. So I can get longitudinal waves in the air. A longitudinal wave is defined when the displacement of the particle is in the same direction as the propagation of the wave energy. So when I talk to you, the particles of air, if you could see them, move backwards and forwards. They don't go from my mouth to you. I mean, this particle pushes that particle, which pushes that particle, which pushes that particle. But the motion of the particles is in direction that the energy is flowing. there need not be anything other than basically, bouncing into each other to cause this wave to work. A great example is sound going through air, going through water, going through solids. Ultrasound. You want to check your pipeline to see if there's any flaws in the welding, do an ultrasound on it. It's great. The other type of wave is called a transverse wave, and that is where the motion of the particle is at 90 degrees to where the energy flows. And that's what we showed you in the spring, where we moved our hand up and down, but the energy went along the spring. So water waves in the ocean, the wave goes up and down, but it seems like the oscillator goes up and down. The particle of water goes up and down, but it seems like the crest moves over the surface.
Just like the last example we did last class, where we had the weight on the spring. So as we maneuver the spring up and down, we would fictionally be creating an oscillator force going out 90 degrees.
You'd be plotting a graph of that oscillation, but if you had a whole bunch of those things connected together, yes, you would see the oscillation go at 90 degrees. If you get away from the shore, if you think about waves in the surf by the beach, they're really complicated. They're actually circular waves. There's actually this really complex motion. But if you go out into deeper water, if you notice, once you get away from the surf, there's not that pushing and pulling on your legs. And basically the crest comes and the crest goes and the crest comes and the crest goes. And you can just bob up and down with it. And you can be a little bit away from the shore and you might not at all be pushed onto the shore. Because although the crest is going to the shore, the particles are not going to the shore. The particles are going up and down. Yeah? So that's a transverse wave. I can represent them. This is a hard thing to represent, isn't it? I'm trying to draw a compression with more particles and a rare refraction with less particles. So it's a bit hard to draw. This is a wave pulse, meaning it's that flick. That's a wave pulse. So this would be a longitudinal wave pulse. If I flick and flick and flick and flick and flick with a regular frequency, I get a longitudinal wave train, like carriage after carriage after carriage after carriage after carriage after carriage after carriage. It's a longitudinal wave train. So a hum, well, a hum would be a longitudinal wave train. It's that continuous pattern. If you like, it's not strictly tuba. That would be much more like a longitudinal wave pulse. It's only a short little click. Yeah. A transverse wave train would be just flick, 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 flick at a regular frequency, and a transverse wave pulse is what we were doing on that slinky. The difficult thing about demonstrating a transverse wave train is that it will then reflect, and we get the reflected wave interfering with the ongoing wave. And they interact in such a way that you get a thing called standing waves, which we'll get to. But from a demonstration point of view, it's showing a pulse is relatively easy because it goes and it comes back. But if I try and show you a continuous wave train, what happens is they interfere with each other and you start seeing a very complicated situation. So for a transverse wave, you need some kind of elasticity. You need some stretchiness. And in water, that's caused by the surface tension of the water. In that spring, it's caused by the spring constant of the spring, and so on. So you will always get some kind of longitudinal wave can go through pretty well anything apart from a vacuum. But a transverse wave can only go through the bits that have elasticity in them.
Yes, sir. I have two questions. One regarding the longitudinal, one regarding the transverse. The first regarding the longitudinal is, as you just mentioned, there's a contingency of the medium. Obviously, anything other than a vacuum. But better the transmission of a longitudinal wave.
Better meaning?
Like in the ocean, you could put a pipe in the water, your ship several miles away.
So you mean in terms of loss of energy or the like? Yeah, that I guess I've never thought about it. I guess that would be true because there's more contact between one atom and another. In a gas, maybe I'll hit that atom, maybe I won't. So as you pump the air out of a bell jar, I would expect the longitudinal wave to just disappear. The energy is still inside the bell. It's just not been transmitted by the... have you ever seen that? If you look online, if you look up bell jar experiment, you can get a bell jar and you have a bell going inside it, and as you pump the air out, the sound disappears because it cannot be transmitted because the density of the gas is getting less and less. Okay?
The question that comes to mind really with regards to that is the inertia of the particles. I mean, I'm bleeding out energy per particle as I attempt to...
So you're talking about different particles now. You're talking about massive particles versus less massive particles.
Well, I mean, the sum total of the particles.
Well, then you're talking about mass density. And I don't want to get bogged down on that there. I mean,
Okay,
that's for another
I should
discussion.
ask later.
So then what about this wave? Was there a question about wave pulse?
Transverse waves, it occurred to me regarding the wave train that maybe that would be like a simulation of, say, noise on a cable. You were mentioning coaxial cable a moment ago. So I was thinking that the inverse, the reflection of the transmission is often interpreted as noise.
So I don't know about noise, but it certainly will interfere with your signal. It may well diminish it. I mean, when you're making connections in transverse, in coaxial cables, you really want to make it so that there's basically as little difference in the impedance between the two parts of it. They will use a lot of technologies to try and get it so that from an electrical signal point of view, it cannot see that connector. Okay? And when they do, like for instance, optical cables, when they do glass fiber cables, they really go to great lengths to make sure that the light is not aware of the fact that those two pieces of glass were at one time separated. So there's a lot of technology in that because you don't want reflection from those connectors. Yeah. Okay, cool. So if we say classify the following types of waves, if I had a single ripple, what would that be? So it would be a pulse, and what kind of pulse would it be? Transverse. And then what about the sound of a continuous whistle? Train, yeah. So just don't skip stuff like that because that's a nice easy point if I give it to you. There's an interesting thing. I want to do a little bit of an aside here, but how do we know that there's a liquid core? So what we think is going on in the Earth is we have the crust, then we have the mantle, then we have a solid core, and we have a liquid core. So this is the liquid core. How on earth do we know? I mean, no one's ever cut the Earth up and...
Well, in Genesis.
So, one of the ways is because of what we just learned about. So we have an earthquake, and the earthquake sends energy, and the energy goes in two forms. It goes as a longitudinal wave, and it goes as a transverse wave. And longitudinal waves will go through anything, whether there's elasticity or not, they'll go through. And transverse waves can only go where there's elasticity. And there's not elasticity in a fluid. So what you see is, we have measuring stations. There's one on the roof of this building. And they're all over the world, if you like, now. They didn't used to be, but now they're all over the world. And what you find is, well, there's a difference in speed. If I take longitudinal versus transverse, the longitudinal is faster. So this is faster. Now, can we kind of intuit that? If I have a bunch of people lined up, and they're all like, My hands are on your shoulders, your hands are on the person in front of your shoulders. So we have a whole bunch of people like connected, and I push the back person. Pretty soon that energy is going to be coming out the front person. Agreed? Because they're all connected, yeah? Compare that with, I got to move you to the side and then move you back again, and you got to move the person in front of you to the side and move you back again, and he's got to move the person to the side. As you go to a transverse energy mechanism, there's delays and delays and delays. So kind of intuitively, I think you can see that longitudinal will be faster and transverse will be slower. And in fact, in geology, they call the longitudinal the primary wave, and they call the transverse the secondary wave. Transverse wave and secondary waves. And the way I remember it is transverse has an S in it, whereas longitudinal doesn't. Doesn't have a P in it either, but you know. If you look here, and the way you know how far away the earthquake was, you look at the time difference between the primary and the secondary, and you say it must be that far away. And you look at the time difference between the primary and secondary, and it must be that far away. And you look at the time difference between the primary and secondary. And that's how they get these things really quite nicely done, because there's so many different seismographic stations all saying it's that far away, and all those lines cross. So they can get this quite precisely by the time difference. But when they go basically around here, they only get the primaries. They only get longitudinal around here. Here they're getting primary and secondary, longitudinal, transverse, primary, secondary, primary, secondary. But round here, they're not getting any transverse waves. And so what that says is the transverse wave couldn't make it through. And what can a transverse wave make it through? A big envelope of fluid. And so that's one of the evidences that there's a fluid layer in the fluid bit in the Earth's core. And then the other thing is we have a magnetic field, and you can generate a magnetic field by having charged particles moving in circles. And so they believe there's an iron core. Why iron? Because it's the most stable nucleus. So we have an iron core, and we have liquid iron around the outside. And so we get that rotation effect, and that causes a dynamo effect, which gives us our magnetic field. So it pieces together, but no one's cut up the Earth to look inside. But it's, you know, it's taught in schools like it's, you know, we know. And we do know. But we do know because there's lots of pieces of evidence pointing towards it. Cool. This slide is really important, actually, because it codifies an awful lot of language. Sorry. It codifies an awful lot of language. It codifies an awful lot of language that we need to think about. And so we have the oscillators on one side, and we did that last time. We have waves on the other side. And first thing I want you to look at is these two graphs. This is a graph of vertical position versus time. And this one here is a graph of vertical position versus horizontal position. And they look identical to a casual glance. And that's a problem, because people tend to misinterpret graphs quite a lot. So let's be careful. Let's draw a kind of like hard line between these two. And we say, well, oscillations, we represent them by a graph of position versus time. So it's an abstraction. It's one particle's history. And we can talk about its amplitude. That's from the equilibrium position to the extreme. In my wife's department, they talk about peak-to-peak amplitude, which is from one extreme to the other, because it's easier to measure on, back in the days when they had chart recorders, it was easier to measure from one extreme to the other. And so people would talk about peak-to-peak amplitudes rather than the amplitude. And of course, in time, people get to the stage where we all know what we're talking about. So why should I say peak-to-peak? Let's just say amplitude, because in this room, that's all that ever means. But then you go to another room, and you got a different tradition. So we've got to be a little bit careful. We don't mean peak-to-peak amplitude. We mean amplitude, and amplitude is from the middle bit to the extreme. And we can talk about the period, that is how long it takes to go from one point to a repeating point, which is crest to crest, or you could have trough to trough. It's not middle to middle. It's middle going downwards to middle going downwards, or middle going upwards to middle going upwards, but it's not middle to middle. That's a common mistake, is people just go middle to middle, and they get half a period. And that's all we really need. But then people say, well, hold on, I want to talk about how many cycles per second I can have. And so we start talking about frequency. And then for various reasons, what we mentioned last time was that the simple harmonic stuff can be described mathematically by the circular motion stuff. And so if we're talking about not cycles, but cycles of a circle, then we can represent how far we get along the cycle by how far we've got around the circle. So times can be represented by angles. And so we start wanting to talk about not just frequency, but angular frequency, where 2 pi radians in one complete circle. So omega equals 2 pi over t, or omega equals 2 pi f. And what I've really ingrained in me is omega equals 2 pi f. And I can figure everything out from there if I get. What's going to happen here is you're going to get confused even after you've learned them a bit. You know, you're going to be under stress and you're going to count, oh, what was that? Because it's a lot of new terminology. So anything you can do to kind of anchor yourself is really useful. So I know that omega equals 2 pi f. I know that f equals 1 over t. So I can say omega equals 2 pi over t, and I'm on my way. I'm going to use omega quite a bit. If I look now at a wave, so now I have a whole family of oscillators. I say that it's a position, it's a graph of y position versus x position, and I'm looking at the one instant for many particles. It's like looking at the side of your fish tank and taking a picture, and at that instant you see all these ripples. It's not the history of one oscillator, it's every oscillator's position now. We can talk about amplitude again. It's from the equilibrium position to the extreme. And we can talk about the wavelength, not the period, but now the repeat distance from middle going up to middle going up, or from crest to crest, or from top to top. That is now a distance, and it's a wavelength measured in meters. If I want to say, well, how many waves, how many wavelengths can I get in 1 meter? Then I can talk about my wave number, which is measured in meters to the minus 1, 1 over meters. Just like frequency should have been measured in 1 over seconds, we call it hertz. But wave number is 1 over meters. And just like we found this angular stuff to be useful, we're going to find angular stuff with this, and we're going to have k, which is our angular wave number. And by analogy, k equals 2 pi over lambda, just like omega equals 2 pi over t. So I can say, oh, well, k equals 2 pi times my wave number. Wave number, I suspect for most people is brand new, and I suspect angular wave number for most people is brand new. So don't let that unfamiliarity cost you. Get familiar with it. Just keep running these analogies backwards and forwards. It'll get easier and easier. And although you're always going to be a little bit uncomfortable, unless you do this for a living, you know, unless you work with waves for a living, you'll always be a little bit uncomfortable with it, but it will be less and less uncomfortable. So sweat the details on this. There was something else I was going to tell you, and for the life of me, I can't remember what it was going to be. Oh, yes. K. Oh, man. And this is not my fault. We just had K in spring constant in the last chapter. And now we're going to be dealing with waves on springs, for example, and we're going to have K again. And that's just the way it is. That's just like, we ran out of letters a long time ago. You know, we went through all the Arabic ones and went through all the Greek ones, and, you know, we're having to reuse them. It's just the way it goes. It's not the end of the world. Context will tell you. You don't get confused about a queue when you, well, that's an English example, a queue when you go to the store and line up, and a queue when you're playing pool. Or you don't get confused about, God, must be a ton of American examples. You don't get confused about, yes, brilliant, yeah. You don't go, you kind of say, do you want a cup of tea? And you go, oh yeah, well, this has got liquid in it. You know from context what it's going to be. It's the same word, but it's used in two different ways. So, you know, this is not the end of the world. But it helps if you kind of like help yourself. So what I do is I don't make up a new symbol for it. But, you know, frankly, you know, my K is like that. And when I'm doing this and I'm concerned, I might do that so that in a derivation I don't get one K confused with another K. You know, that's allowed. You can't call it alpha and mess everybody up because it's, you know, you've got to call it a K. But you can help yourself with it. Use a subscript, you know, KAW for angular wave number. Cool. So analogies, I love analogies. They really help us, especially in physics too. So period is like wavelength, and frequency is like wave number, and angular frequency is like angular wave number. And if you know one set of these pretty well, and you know the analogies, you know the other set pretty well. And I'm not above doing the old SAT questions like period is to wavelength the way that frequency is to ... And then you've got to write in what it is. It's just familiarity. What is the period of an oscillation that completes 5 cycles each second? So visualize. You got 5 cycles, and this is in time, that's in seconds, and oh, okay. So what is the period? And the period is that. Oh, period. And 5 cycles each second is a frequency. Oh, T is equal to 1 over F, which equals 1 over 5 cycles each second, which is 0.2 seconds. Or you can visualize and say, in 1 second, I had 5 of them, so one of them will occupy 1/5 of 1 second. So you might find it's more obvious to you when you think of it graphically. How many people think of it graphically and it's got to go, they go, ah? And how many people, you've got to pick one of these. How many people are happier with the equation? Equation? For me, I just find, I know the math, but I look at that diagram and I go, well, of course, yeah, there's 5 of them per second. It's 1/5 of a second, duh, you know. And it's because I'm a bit more of a visual thinker than I am an abstract thinker. What is the frequency of an oscillation that completes 5 cycles each second? Well, it's 2, 3, 4, 5. There's 1 second. What's the frequency? This frequency is number of cycles per second. Oh, 5 hertz. Yeah. It's just asking you what, I'm just playing with names there. And then what is the angular frequency of an oscillation that completes 5 cycles once per second? So I'm going to say my angular frequency, omega is equal to 2 pi f. I've got that ingrained in my head. So omega is equal to 2 pi times 5, which equals 10 pi, and radians per second. Now, in a test, I want you to work out what the pi is. So that would be 31.2, etc. There'll be times when you leave letters, but I've actually stopped letting people leave the pie, because some people leave it and some people don't. And then the people that don't sometimes make a mistake on that thing, and I catch it, and then I think, well, this guy didn't even try to work it out. So I say, if it's a pie, work it out now. Well, I've done my bit. I'm going to leave you to do these more complicated ones. So let's do them together one at a time, okay? So what is the wavelength of a wave that completes 2 cycles each meter? And I want you to click it in. So did you get clickers? Yeah, so when you got the answer, just click it in and let's see. I would draw a diagram first if I were you. And it's not a position versus time graph. This is a X position and Y position. That's what we're looking at with a wave. And it tells me that there's 2 cycles each meter. And find your first cycle and find your second cycle. And you know that's 1 meter. So then it says, what's the wavelength? So what's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. If you're not going to do it, if you're not going to play, then just click any old thing. Preferably E, but so you go on and you go whatever letter you like. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Go. There we go. That's it. So let's stop this and let's see. Was there unanimity? Let's see. Yes. Okay. So there's no point in me kind of like saying anything. But basically, you know, your wavelength is the repeat, so it's from there to there. And if that's 1 meter, then the lambda equals 0.5 meters. Or alternatively, you can say, I know this is uncomfortable, but you can say, I want to know lambda, and I know that 2 cycles per meter, I know that that is equal to 2 cycles per meter, and I know that now I'm having to do some transferring, and I know that, oh yeah, wavelength is equal to 1 over the wave number. And man, that's uncomfortable. But if I'd said period is equal to 1 over frequency, I wouldn't have batted an eyelid at it. I'm very comfortable with that. I'm not comfortable with that because it's new terminology. So just spend some time and get the terminology, and certainly learn the equivalencies. What is the wave number of a wave that completes 2 cycles each meter? So can you ever got that one for me, please? So now I have, this is 1 meter. This is my Y, this is my X. I want the wave number. Wave numbers like frequency. Wave number is the number of waves in 1 meter. Like frequency is the number of cycles in 1 second. Wave number is the number of waves, wavelengths in 1 meter. So how are we doing? I'm going to give you until 1 minute. Come on, number 9. Come on. Okay. Yes, well done. What did we all say? Oh, a bit more mixed here. So most people saying A. Some people saying C and D. So let's have a look at this. Well, I can, from my diagram, I can see that what is the wave number? What is the wave number of a wave that completes 2 cycles each meter? The wave number is how many wavelengths in 1 meter. So it must be my wave number is equal to 2 per meter, 1 over meter. And I can get that again if I want to think about it. I'm looking for my wave number. I know my wave. I want my wave number. I'm given my wave number in different words, so there's not really any math to do on that one. But the answer's 2 on that. 2 per meter. Yep.
I don't understand the exponent. Is that just notation?
Oh, that means just meters to the. So if something is in per meter, it's 1 over meters, which is meter to the minus 1. It's not mathematical, it's just the terminology of it. That's meters to the minus 1, yeah. But we don't usually see that, which is why it's kind of like triggering, this must be some math thing. And it's just the way of writing the 1 over meters. Then the last one is, what is the angular wave number of a wave that completes 2 cycles each meter? So again, we'll do this together. So this is 1, well actually no, if you want to do it, do it. So why should we take the fun away? And I want to know the angular wave number. So my angular wave number is K. And it's equivalent to my omega. And I know that my omega equals 2 pi times f. So I know that K equals 2 pi times my wave number. And I'll give you, oh, we're done. Sorry, I'm drifting off. Okay. So, where are we? There. So stop it and let's have a look and see what everybody says. Mainly A. And we can get that from, 2 pi times that. So it's going to be 2 pi times 2, which equals 4 pi radians per meter, which is there. And I guess what you could do is you could say 2 pi, 4 pi. Yeah, I mean, you could see it like that as well. 2 pi, 4 pi. Cool. Uncomfortable, mathematically not hard, very uncomfortable. So just watch out for that, okay? Because we're going to use those K, and we're going to use K and mu and omega a lot. We're going to use K and omega a lot. So a bit of a line here. I want to talk to you about a wave, a pulse. I'm not going to do a symmetrical pulse because it gets hard. So I'm not going to do a bit of a sine curve because I want you to see the shape of this thing. So I'm imagining just a positive going pulse. And I take a picture of it and I draw that out. That's the first one. And then a split second later, I take another picture, and a split second later, I take another picture, and so on. I've got 5 pictures there. And I'm showing, by staggering how I see them, I'm showing how that shape, whatever it is, that shape moves further and further and further and further along the x-axis. Okay? And my aim is to develop an equation which will give me the y value at any value of x at any instant in time. So I can say, well, use this value of x, but use that time, and tell me what the y value is of that point in space at that time. So there's 2 things that are changing. There's where I am in x and where I am in time. So I want an equation which gives me the value of y, and it's going to be some function of the position, and it's going to be a function of time. Now remember what we said about our dimensions in physics 1. When you have an equal sign, the dimensions or the units on the left have to equal the units on the right. Agreed? You can't have apples equals oranges. It makes no sense. Apples must equal apples, yeah? But also we said you can't add apples to, ballistic missile. Who cares if you've got 27 apples and 33 ballistic missiles? Adding the two numbers together doesn't tell you anything. So you can only add apples to apples and oranges to oranges. So that means that, again, my units have to be the same in a plus or minus link. I can multiply and divide different units, but I can't add and subtract different units. Just makes no sense. So when I'm writing an equation, I know that my units on the left must equal my units on the right, and every bit of my units on the right. And if my units of the left are in meters, then I know that the bit on the right must be in meters, but time is not in meters. And so I know off the bat, I can't just have something, a number times time. That's not going to work. That's magic. That's not going to work. I got to have the same units in this bit, and the way I get from time to meters is I multiply my time by a velocity. So that's math. The fact that I know that V goes there is like, hey, you got to get back to time. So you got to multiply your time by your, you got to get back to meters, so you better multiply your distance, your velocity by your time. 60 miles plus 60 miles an hour for 3 hours. That's the distance, yeah. Now, why is that negative sign there? That negative sign there is to forewarn you that in the most common example that people think of, which is waves moving to the right, that's going to be a negative sign. That's just to warn you. That's like, hey, watch out for this.
Equation here is to find the instantaneous wave height.
Yes, it's the instantaneous wave height at some position along the x-axis at some time in the future. Okay, so then I say, okay, well, let's play with this a bit. So I'm going to assume that at time equals 0, this is the shape I had. And then I'm picking this point here on the x-axis in both cases, but I'm picking a later time. Time t equals t seconds. And what I say is the displacement on the y-axis depends upon the x location that I picked and also on the time that I picked. So I say, well, y is some function of x and t. The wave function y represents the y coordinate of any point P of the medium at any time. For a wave traveling to the right, I say y equals f of x minus vt. And for the wave traveling to the left, it's f of x plus vt. And the question is why. And so the way I can best describe it is, it's like you are stood here at the x position, and if you look to the left, you see what's coming towards you in the future. So if you're stood there and you want to see what's going to happen in the future, then look to the left. Yeah? That's looking in a negative direction. So for a way, so imagine you stood at the side of the road and there's traffic, and traffic is coming from the left. You don't look to the right to see what's going to happen in the future. You look to the left to see what's going to happen in the future, because that's what's coming towards you. Okay? So if you want to know about the future for traffic traveling to the right, look to the left. And if you want to know about the future for traffic traveling in a negative direction, look to the right. And that's the best justification I can give you for why it's a positive sign or a negative sign. It kind of makes sense. I can't give you this nice, neat mathematical derivation, but does that make sense? It's like, if it's traveling from left to right and you want to know what's going to happen in the future, look to the left, because that's what it's going to arrive. And so that's the game we play. This is a little bit, I'm going to jump if you don't mind, but I will come back to it. Actually, no, I'm going to go back, sorry. Let's just do a little bit of pause on that, because we're into this idea about wave speed. So the frequency is how many waves pass a point each second. Yes, frequency is how many oscillations you get. So I'm used to it for an oscillator. The frequency for an oscillator is how many oscillations you get. But if you imagine, you know, if I'm looking at waves, that's the equivalent of saying how many crests pass me. Yeah, if there was one oscillation, a crest passed me. Two oscillations, two crests passed me. Three oscillations, three crests passed me. Yeah? So, okay, the frequency is how many waves pass each point per second. Wavelength is how long each wave is. So the speed will be that combination. If you imagine the frequency is like, you know what cadence is? I don't know how to spell it. C-A-D-A-N-C-E. Like the marching, it's the frequency, it's the rhythm of your marching, yeah? Is that a C or a K? I don't know which it is.
I think it's a C.
Okay. And so it's like, that's what you get from your frequency. And high frequency, lots of steps. Low frequency, little steps. Fewer steps. And then the wavelength is how big a step is. Well, if I take a lot of big steps, I'm going to go really fast. If I take a lot of small steps, not so fast. If I slowly take big steps, not so fast. If I slowly take small steps, I'm hardly moving. So it makes sense that it's this combination. And if you like, it's 1/seconds times meters gives me meters per second. So that's meters per second, that's meters, that's 1/second. So either way, it all makes sense. And so I get this fundamental equation, which again is burned into my skull, which is V equals F lambda. And that's going to come up for years. You know, it's going to come up all this semester, that's for sure. But that's going to come up for years. Student strides with a step size of 2 meters. So that means my wavelength is equal to 2 meters. And steps at a rate of 8 strides per second, frequency equals 8 hertz. What's its velocity? V equals F lambda. V is equal to 8 times 2, which equals 16 meters per second. Yep, piece of cake. When you deal with it in terms of people walking, it's a piece of cake. Now, I want an equation which is some function of x minus vt for a positive going wave, and y equals some function of x plus vt for a negative going wave. So the first thing I need to do is get the wave shape. So this is the wave shape. This is giving me my value of y as I change the values of x. There's no t in here. It's the wave shape. That's giving me this graph. Now, I'm not using a single pulse now. I'm using this sinusoidal curve. And I decided to start it off at 0 like that. Just like before, I decided to move the block to the right and let it go. Now I'm deciding to set it off like this. And so my math, because of my decision about that last time, I got a cosine for my displacement in time. Now, because of this decision, I'm getting a sine to start off with. Yeah, just my decision. So if you like it, it's going to be, my y is going to be, well, the biggest it can be is my amplitude, but it's modified by this sine function. And it's a sine curve, so it goes from +1 at 90 degrees to 0 at 180 to -1 at 270 degrees to 0 at 360. Oh, all I need to do to get this thing to work is I want to express my position as a fraction of a wavelength there are 2 pi radians in one wavelength. So if x is the same as lambda, I get 1. 1 times 2 pi is 2 pi, which gets me to there. If x is half a wavelength, then I get a half times 2 pi is pi, which gets me to there. So it's a really clever kind of scheme. It says this pattern just repeats, and all I got to do is figure out how much distance there is in one wavelength. Represent that distance in terms of a fraction of a wavelength, and I get my equation. Because it's going to repeat. If this is 7 meters, that's going to be 14 meters. Okay. So, although, and it's worth playing with, although it might not seem like it at the beginning, I want to clean this up a bit. This is a really nice way of expressing the shape of my wave. It says, oh, it's going to be a sine curve, it's going to have an amplitude of A, and it's going to have the angle will depend upon, where you are in x depends upon x versus lambda. Yeah. Are you at the whole wavelength position, or are you at 2 wavelengths, are you at 17 and a half wavelengths? We can figure out, because we're starting off like this. If you're 17 and a half wavelengths down there, I go 17 and a half wavelengths down there, and I can figure out where I'm at. So it's a way of getting the shape. Just play with it when you go home and you'll see it. Now, I want to get time involved in this. And the way I do that, I've got to be careful. Oh man. I might run out of time. Oh yes, almost. Now I'm going to put time in this. And so I need something which basically represents time. Can you see how velocity times time is a position? So what I've really done there is I've said, oh, let's include in this something to do with position, and I'm going to have minus, I'm going to say, well, it's going to be Vt over lambda. Again, the distance that this Vt represents is ratio to the wavelength. The x position is ratio to the wavelength, so I know how many wavelengths this represents. The distance caused by time is ratio to the wavelength, so I know how many wavelengths that represents. I'm looking to the left because the wave is going to the right. So I end up with this expression, y equals a sine 2 pi x over lambda minus Vt over lambda, and I'm going to say x minus Vt over lambda. Okay, that's an important equation. Next, remember that V is equal to, let's have a look, V is going to equal to f lambda, so it's going to be lambda over t. And so what I can do is I can say, rather than that V, I can say lambda over t. Can you see how those lambdas cancel out? So I end up with 2a sine 2 pi x over lambda minus t over big T, the period. And if I remember that k equals, what was it, 2 pi over, let's have a look, I've got to do some thinking here. Omega equals 2 pi f, k equals 2 pi that, which equals 2 pi over lambda, so that's going to be over lambda. So therefore, I get y is equal to a sine 2 pi over lambda is going to be k, not spring constant but angular frequency, but angular wave number. And if I also know that omega equals 2 pi over t, I end up with omega there. The take home is I need you to know that y is equal to a sine 2 pi over lambda x minus vt, or y is equal to a sine kx minus omega t. We use both of those. We use this one slightly more than that one. Okay. And we have developed an expression which gives us our y displacement at any point at any time in the future. Okay. Typical question. I tell you k, I tell you omega, I give you a, I ask you for the rest. It's typical like that. Okay. If I do not start off with this perfectly aligned thing where I start going positive when t equals 0 and all at the origin, if I mess with it, how do I account for that? I put in a phase angle. And so I get y equals kx minus omega t plus phi. It's done. Yeah? Cool. Okay. I'm going to stop there.